Hello, wonderful calculus students, and welcome. Again, I am aware that this is a very strange way to go over notes, to literally just have a picture and be zooming in on crap. I get that that is not traditionally how this is done. I get that it is probably not ideal, but I believe I can still offer you some pretty good insight. So if you wanna hang in here, just hang in here and see if you can learn a few things. Today we're going to be covering a couple topics on sequences and series, more specifically series. We're going to be going over the integral test for convergence and then remainder estimates of convergent series. We're going to start with the integral test. I'll put a timestamp in the description as to when I start discussing remainder estimates. So let's jump right in with the integral test. This is a pretty simple test. Simply stated, the integral test says that if you have the summation of a sub n, let's pretend a sub n is 1 over 3n plus 1, just because that's what we have in the example. So you have the summation of a sub n. Now there's a lot of ways eventually that you can find the convergence of this, whether it converges. But there's not a lot of ways that you can find out what it converges to. That is something the integral test is very good for, because what the integral test says is that if the summation of f, or rather the integral from 1 to infinity of f of x, where f of x in this case, just as an example, would be 1 over 3x plus 1. You just replace the n's with the x's. It's really simple. The integral test says this integral from 1 to infinity of f of x, if it converges to a number, the series converges to that number. So just pretending this is not the case. You'll find out very soon this is not the case because we're going to go through this example. But if the integral from 1 to infinity of 1 over 3x plus 1 was equal to 1/4, then guess what? The summation from n equals 1 to infinity of 1 over 3n plus 1 would converge to 1/4. So let's dive right into this example, actually talk about it. First thing you want to note, you always want to start with the nth term test. I would not recommend always writing this down because it's very obvious that n goes to infinity, and so therefore the whole thing goes to 0. So the limit as n goes to infinity of 1 over 3n plus 1 is 0. Don't waste your time writing that down, but always make a mental note, because you always mentally at least want to start with the nth term test. It's just a very easy one, so always mentally start with that. So that fails. Let's pretend you want to know where it converges to. We're going to try the integral test. So, and you always want to write this down to be all prim and proper, you're going to let f of x equal 1 over 3x plus 1. Basically, all you did was take a sub n and put x's where there were n's. That's pretty easy. You should note x cannot equal negative 1/3. That would make the denominator go to 0. It would be undefined. However, that's not an issue because x has to be greater than 0. I wrote that's why. That's why. We know that x has to be greater than 0. It's going from 1 to infinity, so it's not going to be an issue. But it is a good thing to note. So, to use the integral test, what do you have to prove? Luckily on this one it's easy, but you always have to prove that f of x is positive. Well, x is positive, and everything else around it is positive. Yeah, f of x is going to be positive. It's decreasing. Well, the numerator is staying the same. The denominator is growing larger and larger and larger. Yeah, it's decreasing. It's continuous. We proved that right here. The only place where it's not is negative 1/3, and that's not on the interval. You always have to prove those things. On this problem, it's pretty easy. On some other problems, it can be a little more of a challenge. But always keep that in mind. You have to prove that it's positive, decreasing, and continuous to use the integral test. Otherwise, the integral test will not work. So, we're going to let f of x be 1 over 3x plus 1. So we take the integral from 1 to infinity of f of x dx. That is the integral from 1 to infinity of 1 over 3x plus 1 dx. Remember that the proper way to do this is to take the limit as a goes to infinity of 1 to a over 1 to a of f of x. Sorry, lost my words there. So we're going to take the limit as a goes to infinity of the integral from 1 to a over 3x plus 1. That's just a simple u substitution. Like I said, this is a pretty easy problem. U is going to be 3x plus 1. Du is 3dx. Therefore, 1/3 du is dx. So you plug that in, you get the limit as a goes to infinity. Remember that u equals 3x plus 1. So now we're plugging in for u. That's going to be the integral from 3x was 1, so 3 times 1 plus 1. 3a was infinity, so x was a, so that's the integral from 3 times 1 plus 1 to 3 times a plus 1 of 1 over, plugging in u was 3x plus 1, so that's going to be 1 over u times 1/3 du, because that is what dx equaled. So we get all that good jazz. We simplify it a little. I'm not going to insult your intelligence too much. You can figure out what that ends up being. It's right here in case you can't see it. If you didn't get that, well, maybe you should learn a little more basic math before you do calculus. I'm just messing with y'all. But anyways, so now we have, after we take the actual integral, integral of 1 over u becomes ln of the absolute value of u. So we get 1/3 limit as a goes to infinity of ln absolute value of u from 4 to 3a plus 1. So that becomes 1/3 limit as a goes to infinity ln of 3a plus 1. It's positive, so you don't need the absolute value anymore, minus ln of 4. Well, that's an actual value, ln of 4. That is not an actual value. That is going to diverge, because that will basically be the limit of infinity, the limit of, or the ln of infinity. So the ln of infinity is infinity. That is diverging. That should be pretty obvious. You should be able to see that. It's 1/3 times infinity, which is still infinity, so it diverges. So therefore, because you should always write this too, you should always give a conclusion. You shouldn't just say diverges. You should give a proper conclusion at the end. The integral from 1 to infinity of f of x dx diverges. So the summation from n equals 1 to infinity of 1 over 3n plus 1 diverges by the integral test. That is the only example I'm going to give you on that one. I hate this test. That is why that's the only example I'm going to give you on that one. This is an awful test if you have some difficult functions. And I think there's almost always, not always, but there is typically a test that is a lot easier. The only reason you would use this test is if you had to know what something was converging to, because sometimes the integral will come out to 1/2. So you know that the function is going to, or the series is going to converge to 1/2. It's good for that. But if you just need to know convergence or divergence, I would absolutely not recommend this test. It is a pain most of the time. So there you go. There you have it, the integral test. Now we are going to move on to remainder estimates. So, remainder estimates. What is that? That basically tells you if you're going to approximate the sum, how close are you going to be exactly? So, R sub n equals the remainder estimate. That is, R sub n is your actual remainder. There is a proof above in my notes. I didn't take a picture of that because it is long and it is a little confusing. And if you want to learn that on your own, feel free to look it up somewhere else. You can find it all over the place, that proof. But like I said, it is long, it is complicated. I just want to dive right into the meat of this, give you what the remainder actually is. So, the remainder of n, so you're estimating your sum out to n terms. So if you're going to take the estimate of the summation of a sub n to n equals 20, then that would be remainder 20, R20. Your remainder out to n terms is going to be greater than or equal to, that's over here, the integral from n plus 1 to infinity of f of x dx. So I'll say that again. The remainder out to n terms is going to be greater than the integral from n plus 1 to infinity of f of x dx, where f of x, like the last time, is basically going to be a sub n. F of x is basically going to be your given series, except with x's instead of n's. That is all that is. It is going to be less than the integral from n to infinity of f of x dx. So just take a minute to look at that. The integral from n plus 1 to infinity of f of x dx is less than the remainder, which is less than the integral from n to infinity of f of x dx. Now this sometimes confuses people because people see that's an n plus 1 and that's an n, and they think, well, shouldn't n plus 1 be bigger than n? Think about it like this. This is an integral. You're taking the integral from a point further back over here because n is not as far as n plus 1. That just makes sense. So if you're taking the integral from further back, there's a little more area included, right? Yes, of course there is. So this is actually going to be bigger than this. It's really easy to get that confused, so I just thought I would clarify very quickly. We also have this truth that r sub n, the remainder, equals the actual sum minus the sum out to n terms. So therefore, if you're plugging in here, you get s minus s sub n it's the same thing. I'm not going to take the time to say all of that. You've got this statement right here, that r sub n is greater than the integral from n plus 1 to infinity of f of x and less than the integral from n to infinity of f of x. It's the same thing, except that you wrote s minus s sub n. But that leads us to the conclusion that the sum is going to be greater than or equal to the sum out to n terms plus the integral from n plus 1 to infinity of f of x. And it's going to be less than, the actual sum is going to be less than the sum out to n terms plus integral from n to infinity of f of x dx. I hope that was an adequate explanation of the basics. I know talking about it doesn't necessarily do a whole lot of good, so let's jump right into an example. So we have the summation from n equals 1 to infinity of 1 over n to the fourth. Part A, what is the maximum error in approximating the sum of the summation from 1 over n to the fourth using 20 partial sums? So that is up to s sub 20. That's basically what that means. 20 partial sums, that is up to s sub 20. So what I wrote out here is basically how you're going to break this down. It's the summation of 1 over n to the fourth. I just wrote out some terms. If it goes out to 1 over n to the fourth, that's going to be your nth term, so your 20th term. So I could have written 1 over 20 to the fourth. That is something I could have written. That would have totally been an option because n is 20 in this case. So that is your sum sub 20. This portion right here, 1 plus 1 over 16 plus 1 over 81 plus 1 over 4 to the 4 plus all the way out to 1 over n to the 4, which is 1 over 20 to the 4. That is out to the 20th partial sum. So that is going to be s sub 20. Everything else is your remainder. Does that because your full series is all of that. It's going to infinity. So out to 20 is your partial sum, and then from 21 on is your remainder, which is going to be the remainder sub 20. And that's all the terms starting from the 21st term all the way out to infinity. That's all this little blurb is explaining that. So now let's actually jump into the problem. The remainder such that n equals 20. Well, the integral from n plus 1 to infinity, so 20 plus 1 to infinity of f of x dx is going to be less than or equal to r sub 20, which is going to be less than or equal to the integral from n, which is 20, to infinity of f of x dx. You have to say let f of x equal 1 over x to the fourth. Remember, that is basically the partial sum that you're given, or the series that you're given, rather, not the partial sum, the series that you're given, except x's are replacing the n's. So now you can write this as the integral from 21 to infinity of x to the negative 4 dx, which is less than or equal to the remainder such that n equals 20, which is less than or equal to the integral from 20 to infinity of x to the negative 4th dx. If you're looking for the maximum error, you only need to analyze the right side. Why? Well, because obviously that is the bigger side. So it is going to have the maximum error. It's the furthest right in an inequality. Therefore, it's going to be the biggest. So the left-hand side is basically null and void when you're only analyzing the biggest error. That will come from the right-hand side. So let's analyze the right-hand side. R sub 20 is going to be less than or equal to the integral from 20 to infinity of x to the negative fourth. So you go through this just like you go through any infinite limit, which hopefully you know. If you've made it this far in this video and you don't know how to do infinite limits, there is some kind of problem. So you're going to take the limit as a goes to infinity of 20 to a, x to the negative fourth dx. This is not that hard of an actual integral. It becomes negative 1 over 3x cubed from 20 to a. You're still taking the limit as a goes to infinity. Then you plug in and you get that this goes to 0. I'm not going to insult your intelligence. You can solve this by yourself. Minus a negative 1 over 3 times 20 cubed, which just becomes 1 over 3 times 20 cubed, which is approximately 0.000042. So that's how much remainder you have. You have a pretty accurate answer. It is accurate out to 4 decimal places before there is any difference at all. So now you can actually use that to find the partial sum, or to approximate the sum rather. So let's move on to that. That will be part B. Using n equals 20, estimate the actual summation. So the actual summation is s sub 20. It's the same thing as before, except now you're adding s sub 20 to both sides. That's the best way to say that. It's the same thing as the remainder, except you're adding s sub 20 to both sides. So you are literally going to get the sum is approximately s sub 20 integral 21 to infinity x to negative 4 dx. It's greater than that value, and it's less than the value of s of 20 plus integral 20 to infinity of x to the negative 4 dx. So now you can find s of 20 just with a calculator. That's pretty easy stuff. You do not want to take all those partial sums. That would be a nightmare to add up all of those individually. So just use your calculator unless your teacher tells you not to, in which case I am so sorry for you. So just use your calculator to find s of 20. That is literally just the summation n equals 1 to 20 of 1 over n to the fourth. It comes out to that number right there. I'm not going to take the time to say all of that. You've got it right there. You can write it down if you want. You can pause the video, write it down. We're moving on. So you've got s sub 20. And now all you got to do is add it to the integral of 21 to infinity of x to the negative 4 dx on the left-hand side, and add it to integral 20 to infinity x to the negative 4 dx on the right-hand side. That is all you have to do. It's pretty simple. I actually went through and solved this again. You did not have to do that necessarily. We have already solved at least the right-hand side. We have already solved the integral from 20 to infinity in part A. It was this. It was 0.000042. You need to solve the left-hand side, but you've already taken the integral. It should be pretty easy. I'm not going to take the time to explain that because you guys have already done that in part A if you're following through this example with me. I'll just go ahead and tell you, and I've got the work right here if you want to pause it and make sure that you get it right. But it ends up being the left-hand side, integral 21 to infinity of x to the negative 4 dx, ends up becoming 0.000036. That's what it ends up becoming. So now we're going to add these values together. Now we're going to add this is s sub 20 plus the integral. This is the integral 21 to infinity of x to the negative 4 dx. That's going to be on the left-hand side, and then on the right-hand side, we just add this is s sub 20 plus this is the integral from 20 to infinity of x to the negative 4 dx. And this is what we get after you just punch that in your calculator. Notice that is pretty darn accurate. There are 5 whole decimal places before anything is different in these two answers. That is a very accurate answer, accurate to 5 decimal places. And there you go. That is how you take, that is how you get an estimate and a remainder estimate, and how you can approximate a partial sum. Even if you can't find the actual sum, you can approximate by taking integrals, and you can get an answer that, as you can clearly see, is very, very close to the actual sum. That is obviously an answer that is very close to the actual sum. So that is all I have for today. If you have any questions, feel free to leave a comment. I will answer to the best of my ability. And I hope, despite the odd formatting of this video, that you were able to learn something. That is obviously the goal of recording this. Like I said, if you have any questions, feel free to ask. And that's all I got, people. Peace out.